Good morning, everyone. Today I will be presenting on the tuner field effect transistor (TFET), which is one of the most promising candidates among beyond CMOS devices. This presentation is based on several recent research papers. Throughout this presentation, I will first explain why TFETs were introduced, then discuss their structure and operating principle. After that, I will summarize the key materials and fabrication methods reported in the literature, analyze their performance, compare them with conventional MOSFETs, and finally conclude with their advantages, current challenges, and future applications. Before we look at how a TFET works, it is important to understand why researchers start developing this device. For decades, the semiconductor industry has relied on continuous MOSFET scaling, following Moore's law. By reducing transistor dimensions, engineers have been able to integrate more transistors onto a chip, increase computing performance, and lower manufacturing costs. Today, commercial transistors have already been scaled to well below 20 nanometers. However, once MOSFET enter the nanoscale regime, several fundamental limitations begin to appear. The first limitation is short channel effect. As the channel length becomes shorter, the gate loses some of its abilities to control the channel. This leads to problems such as threshold voltage drop-off, drain-induced barrier lowering, and increased leakage current. The second challenge is gate oxide tunering. To maintain gate control, the gate oxide has become extremely thin. When its thickness approaches only a few atomic layers, electrons can channel directly through the oxide. This produces gate leakage current, which increases static power consumption even when the transistor is switched off. Another important limitation is the 60 mV per decade saturation swing limit. Conventional MOSFETs switch by thermionic emission, and this physical mechanism limits how sharply the device can transition from the off state to the on state. Because of this limit, reducing the supply voltage also reduces the on current, making it difficult to improve both energy efficiency and performance at the same time. These challenges motivate researchers to explore alternative transistor technologies. One of the most promising solutions is the TFET. Unlike a MOSFET, a TFET uses band-to-band tunering instead of thermionic emission. This different switching mechanism enables operation at much lower supply voltage while maintaining extremely low leakage current, making TFETs particularly attractive for ultra-low power electronics applications. This is the research paper I use for these presentations. Now that we have discussed why TFETs are needed, let's examine their device structure. At first glance, the overall layout looks quite similar to a conventional MOSFET because both devices have a source, a channel, a drain, and a gate electrode. However, the key difference lies in how these regions are arranged and how current is generated. As shown in the figure, this is an N-type TFET, which has a MP plus source and intrinsic and an N plus drain. This is commonly referred to as a PIN structure. In contrast, a conventional M-channel MOSFET typically use an N-plus source P-type body and an N-type N-plus drain. The gate electrode is placed above the intrinsic channel and is separated by a thin gate oxide. When a gate voltage is applied, the electric field modifies the energy bands near the source channel junction. Unlike a MOSFET, the most important region in a TFET is the source channel junction. This is where band-to-band tunering takes place. Once electrons tunnel from the balance band of the source into the conduction band of the channel, then move toward the drain under applied drain voltage, creating the current. This means the drain mainly acts as the collector of the tuner carriers, while the gate controls whether tunering can occur. So, although the physical structure appears similar to a MOSFET, the current transport mechanism is completely different. A MOSFET relies on thermionic emission, where carriers need enough energy to overcome a potential barrier. In contrast, a TFET generates current through band-to-band tunering, where carriers pass directly through the energy barrier instead of going over it. This unique operating mechanism is what allows TFETs to achieve a saturation swing below the conventional 50 millivolts vertical limit, making them highly attractive for ultra-low power applications. Now that we have seen the basic structure of a TFET, let's move on to its operating principle and see how band-to-band tunering actually occurs when different voltage are applied. First, I would like to explain the basic operating principle of a TFET. A TFET is based on a reverse bias PIN structure, unlike a conventional MOSFET, where there is no gate voltage. The device remains in the off state assumed in the upper energy band diagram. The source balance band and the channel conduction band are separate, since there are not a variable energy state for electron to channel into. Band-to-band channeling does not occur. As a result, only a very small leakage current flows through the device. When a positive gate voltage is applied, the situation changes. The gate creates an electric field that modifies the energy bands near the source channel junction. Once the conditions are suitable for tunneling, electrons move from the source into channel through band-to-band tunneling instead of flowing over the energy barrier. These tunneled electrons are then collected by the drain, producing the Ohmstate current. So unlike a MOSFET, which depends on thermionic emission, the switching operation in a T-FET is entirely controlled by band-to-band tunneling. Now let's look more closely at how the switching process actually happens. The key factor is the gate voltage. As the positive gate voltage increases, the electric field bends the energy bands in the channel downward. This band bending makes the tunneling barrier at the source channel junction progressively thinner. Eventually, the source balance band aligns with the channel conduction band, as shown in the lower diagram. Once these energy bands overlap, electrons can tunnel directly through the barrier by band-to-band tunneling, which is highlighted by the red circle in the figure. After channeling into the channel, the electrons are pulled towards the drain by drain voltage, generating the Ohmstate current. This is the fundamental difference between a TFET and a MOSFET. A MOSFET requires electrons to gain enough thermal energy to cross the energy barrier. In contrast, a TFET allows electrons to channel through the barriers using quantum mechanical tunneling. Because the switching process is no longer limited by thermionic emission, TFETs can achieve a sub-threshold swing below 60 mV per decade, making them highly suitable for ultra-low power electronics applications. Next, I will introduce the materials verification technique that researchers use to improve TFET performance. Based on the three references I reviewed, the development of TFETs has mainly focused on two aspects: selecting suitable semiconductor materials and developing fabrication techniques that can improve tunneling efficiency while remaining compatible with semiconductor manufacturing. First, let's look at the materials. Silicon was the earliest material used for TFETs because it is already well established in the CMOS manufacturing. It is inexpensive, reliable, and can be integrated into existing fabrication lines. However, silicon has an indirect band gap, which limits the probability of band-to-band tunneling. As a result, silicon TFETs usually suffer from a relatively low Ohmstate current. To overcome this limitation, the researchers introduced silicon germanium. Since germanium has a smaller band gap than silicon, the tunneling barrier becomes thinner. This allows carriers to tunnel more easily, increasing the Ohm current while still keeping the device compatible with CMOS technology. The next step was use of good 3 and 5 compound semiconductors, such as indium arsenide, indium gallium arsenide, gallium arsenide antimonide, and indium phosphide. These materials have narrow direct band gaps and much higher carrier mobility. Because of these properties, they provide much more efficient band-to-band tunneling, resulting in higher drive current and a lower saturation swing compared with silicon-based TFETs. More recently, research has shifted towards two-dimensional materials, including molybdenum disulfide, tungsten disulfide, tungsten diselenide, base phosphorus, indium selenide, and tin diselenide. These atomically thin materials offer excellent electrostatic control over the channel, suppress short channel effects, and enable deeper switching characteristics. They are considered one of the most promising material systems for future ultra-low power TFETs. Overall, the material development has progressed from conventional silicon to silicon germanium, then to group 3 and 5 semiconductors, and finally to two-dimensional materials, with each generation aiming to improve tunneling efficiency and reduce power consumption. Although group 3 and 5 TFETs generally provide the highest on current because of their narrow direct bandgap, they are expensive and difficult to integrate with existing CMOS technology. In contrast, silicon germanium offers a compromise between performance and CMOS compatibility, while 2D materials show the greatest long-term potential but remain limited by fabrication challenges. Besides material selection, the fabrication approach is equally important because the performance of a TFET depends heavily on how effective the tunneling junction is formed. The first approach is silicon-on insulator based TFET fabrications. Silicon-on insulators are threads provide better electrostatic control and reduce leakage current while maintaining compatibility with existing CMOS fabrication technology. To improve to further improve tunering efficiency, researchers developed silicon and germanium heterojunction fabrication using selective epitaxial growth. By forming a silicon germanium junction with a controlled germanium concentration, the tunering barrier becomes narrower, making band-to-band tunering easier and increase the ohmstate current. For higher performance device, good 3 and 5 heteroepitaxial growth is used. This progress creates a broad interface between materials such as indium gallium arsenide and gallium arsenide antimonide, allowing carriers to tune them more efficiently and producing higher drive current. Another important technique is the 2D band-ways heterostructure fabrication. Instead of growing conventional semiconductor junctions, different atomically thin materials are stacked together to form clean interface with barely few defects. This improves the electrostatic control and enhances tunering behavior. Researchers have also explored vertical nanowire or gate all-around defects. In this structure, the gate completely surrounded by the channel. So the gate completely surrounds the channel, giving much stronger control over the tunering region. This shortens the tunering distance, suppress short channel effects, and improve overall device performance. Another architecture is the FinFET-based TFET, where multiple gates are used to control the channel from several sides. Compared with a planar TFET, this design offers better electrostatic integrity and improved switching behavior. Finally, Shang and colleagues proposed quantum well group 3 and 5 heterostructure, where precisely engineered layers create an even more efficient tunering junction. This further enhanced tunering efficiency and is considered a promising direction for next generation TFETs. When comparing the three studies, we can clearly see that each paper focused on a different strategy for improving TFET performance. The silicon-based work emphasized CMOS compatibility and manufacturing practicality, making it easier for industrial adoption. In contrast, the good 3 and 5 heterostructure research prioritized achieving a higher ohmstate current by enhancing band-to-band tunering through narrow bandgap materials. The study on two-dimensional band-away heterostructure takes a different approach by using atomically thin materials to improve electrostatic control while suppressing short channel effects. Together, these studies demonstrate that there is no single perfect solution. Instead, researchers are balancing three key objectives: performance, manufacturability, and power efficiency. After discussing the material and fabrication techniques, I would like to compare the performance of TFET with that a conventional MOSFET using several important performance metrics. The first metric is the shut threshold swing, which indicates how efficiently a transistor switches from the off state to the on state. For a conventional MOSFET, the minimum saturation swing is limited to around 60 millivolts per decade at room temperature because it relies on thermal emission. In contrast, TFET operates through band-to-band tunering, allowing it to achieve a saturation swing below 60 millivolts per decade. This means TFETs can switch on more sharply and operate at lower supply voltage. The next step is the next metric is the ohm to off current ratio. A crude transistor should have a higher ohm current for fast operation while maintaining a very low off current to minimize leakage. According to the literature, TFETs can achieve an ohm to off current ratio between 10 to the 6 and 10 to the 9, which is generally higher than 10 to the 4th to 5 times 10 to the 7th report for conventional MOSFET. A higher ratio improves switching reliability and reduce unwanted leakage. Looking specifically at the off-state current, TFET has a significant advantage. Since current only flows when vent-to-vent tunering occurs, the leakage current in the off-state is extremely low. As a result, standby power consumption is greatly reduced, making TFET particularly attractive for the powered and always-on electronic system. However, TFET is not perfect. One of its biggest limitations is the off-state current. Although TFET is very energy efficient, its ohms current is still lower than that a conventional MOSFET because the tunering probability is relatively small. This limits its switching speed and overall drive capability. Finally, because TFET can achieve a steady saturation swing, it can operate at a lower supply voltage. Lower operating voltage directly translates into lower energy consumption, which is one of the main reasons TFET is considered a promising candidate for future low power integrated circuit. However, this performance improvement comes with important trade-offs. While Group 3 and 5 and two-dimensional material TFETs can achieve steeper threshold swing and higher ohm current than silicon-based TFETs. They are generally require more compressed fabrication process and are less compatible with today mature CMOS manufacturing technology. On the other hand, silicon and silicon germanium TFETs are easier to integrate into existing production line, but their own stack current is usually lower. Therefore, future TFET developments is not simply about maximizing performance, but also finding the best balance between device performance, fabrication complexity, and manufacturing cost. This table summarizes the overall comparison between TFET and conventional MOSFET. The most fundamental difference is their switching mechanism. MOSFET operates by thermionic emission, where carriers need enough thermal energy to overcome an energy barrier. TFET, on the other hand, use band-to-band tunneling, where carriers can tunnel through the energy barrier instead of going over it. This difference is the key reason why TFET can overcome the 60 millivolt per decade limitation of MOSFET. As shown in the table, TFET performs better in several important aspects. It has a steeper saturation swing, much lower leakage current, lower static power consumption, and can operate with a lower supply voltage. This characteristic make TFETs an excellent choice for ultra-low power device, such as Internet of Things device, wearable electronics, and energy-efficient processors. However, MOSFET still has several important advantages. It provides a higher ohmstat current, which allows faster switching performance. In addition, CMOS technology has been optimized over several decades, so MOSFET fabrication is more mature, more reliable, and less complex than current TFET purification processes. Overall, TFET offers outstanding energy efficiency because its deep switching behavior and extreme low leakage current. However, improving the ohmstat current while maintaining low power consumption remains one of the biggest research challenges. For this reason, current research focuses on new semiconductor material, heterojunction engineering, and advanced device structures such as vertical TFETs and gate-all-around architectures. These approaches aim to increase tunneling efficiency while preserving compatibility with existing CMOS manufacturing. To conclude my presentation, TFET has emerged as one of the most promising beyond CMOS devices because it addresses one of the biggest challenges in modern electronics, which is reducing power consumption. One of its greatest advantages is its ability to achieve a saturation swing below 60 millivolt per decade. This allows the transistor to operate at a much lower supply voltage compared with conventional MOSFETs, resulting in significant energy savings. Another important benefit is its extremely low off-stack leakage current. Since currents only flow through band-to-band tunneling, standby power consumption is greatly reduced. This makes TFETs particularly suitable for battery-powered and always-on electronic systems, where energy efficiency is a priority. However, TFETs still face several challenges before it can be widely adopted. The biggest limitation is its low ohm-stack current, which restricts switching speed and makes it less suitable for high-performance computing applications. In addition, TFET fabrication requires precise material engineering and abrupt source-to-channel junctions, making the manufacturing process more complex than conventional CMOS technology. Achieving large-scale integration while maintaining consistent device performance also remains a significant challenge. Despite these limitations, ongoing research is making steady progress. Researchers are exploring heterojunction designs and group 3 and 5 semiconductor materials to improve ohmstat current. Advanced architectures such as gate-all-around and vertical nanowire TFETs are also being developed to enhance electrostatic control and tunneling efficiency. Looking ahead, TFET has a strong potential in applications where low power consumption is critical, including Internet of Things devices, wearable electronics, biomedical implants, and AI systems. In conclusion, based on the literature review, TFET is unlikely to completely replace conventional MOSFET in the near future because CMOS technology still offers superior drive current and manufacturing and maturity. Instead, TFET is expected to complement CMOS in applications where ultra-low power consumption is more important than maximum processing speed. This highlights that future semiconductor technology will likely involve the coexistence of multiple device architectures, each optimized for different application requirements. That concludes my presentation on tuner field effect transistor TFET. Thank you for your attention. I will be happy to answer any questions.